So here I wanted to go ahead and just look specifically at uncompetitive inhibition and what we actually have with an uncompetitive inhibitor. Uncompetitive inhibitor is going to bind to the enzyme substrate complex, but not to the free enzyme. So that's where we get this kind of flow chart, if you will. So phase 1, phase 2, and phase 3. Phase 1 is where your enzyme is going to bind the substrate. Phase 2 is where that uncompetitive inhibitor is actually going to act. It's going to bind to that ES complex, and it's basically going to prevent, or ideally prevent, the formation or completion to phase 3, where our product is actually released. Okay, so now what this is going to do is this is going to cause a reduction or a decrease in both your maximum velocity and your Km. Okay, so now how does that going to happen? It's a little bit weird, but this is what's going to take place, or this is what an uncompetitive inhibitor does. An uncompetitive inhibitor, well, it's going to sequester your free enzyme in this EIS or ESI complex. You'll use that ESI kind of interchangeably. And so what that's going to do is it's going to diminish the amount of free enzyme that's present. And so what that is apparently going to do, or what that seemingly does, is it causes a reduction in your Km. Now that's a little bit confusing because reduction in your Km, you could argue that's a good thing, but well, in this case, a reduction in your Km, it does increase your enzyme's affinity for the substrate, but the amount of our free enzyme has gone down because basically what we're doing is we're sucking up that free enzyme, or that enzyme, our enzyme pool as well as our substrate pool is being sequestered more or less in this ESI complex. Okay, so the effect of an uncompetitive inhibitor cannot be overcome by high concentrations of your substrate because, if anything, well, Km goes down, so enzymes affinity, or substrate affinity, it goes up. Okay, so it seems a little bit weird, but that's actually what's taking place. Now, graphically, what that is going to look like is something like this. So we've got two different lines on this graph, and we've got the absence of an inhibitor right here, and then the presence of an inhibitor right here. So what we see is we see a change in y-intercept and a change in x-intercept. Now, what's important here is, well, that takes into consideration our inhibitor. Okay, now what this tells us is, or what these differences on these graphs basically amount to, is it gives us a little bit of an affinity, or gives us a little bit of an idea of how our affinity for our substrate has changed. Likewise, it likewise shows us what our Vmax difference is. Okay, so one of the things that you can do with this is you could take into consideration, well, if you know what this value is right here, let's say it's 3 or something like that. 3 is equal to our Vmax. We already know what our Vmax of our enzyme is, over 1 plus our inhibitor concentration divided by our Ki. So this does give us a mechanism to solve for our Vmax, because in every single one of these trials we would have our inhibitor concentration. Likewise, we have a little bit of an idea right here. So again, if we had an actual value, let's call it -3, that -3 is equal to our Km, or sorry, our -1 plus our inhibitor concentration over our Ki divided by our Km. Okay, so this graph shows us all that information and how our relationship has changed. Because if you remember, if you recall from our original view of our graphs here, our y-intercept is equal to 1 over Vmax. Our x-intercept, a negative value, is equal to -1 over our Km. Okay, so essentially with an uncompetitive inhibitor, you can calculate your Ki a couple of different ways. If you determine the y-intercept with and without the inhibitor present, you can plug that information into this equation right here. Let me switch to the pen and yellow. And now I'm going to go with, let's go with blue. if you know your y-intercept with and without, that's what you're doing. If you determine the x-intercept with and without the inhibitor, you can plug that in down here. There we go. So no inhibitor plus your inhibitor. If you had these values, you can plug in a number for that and ultimately come up with something that gives you your approximate Ki. I want to go ahead and solve for this. And so what I want to do is I'm going to use the first equation. Ki is equal to my inhibitor concentration, which is 2 millimolar, 2 divided by, now I've got a ratio, my y-intercept with my inhibitor divided by my y-intercept without my inhibitor. And so that's going to be 20 divided by 10 minus 1. Okay, so ultimately that plays out as 2 over, well, 20 divided by 10, so that's 2 over 1. So that's going to be 2 divided by, call that 2 minus 1, which is equal to 2 divided by 1 equals 2. My Ki, therefore, is that. Okay, now my Ki solving in the other way. Ki is equal to, again, 2 millimolar, because that's my inhibitor concentration. And now my x-intercept is, let's see, that's going to be -2 over -1 minus 1. Okay, so these are basically, those negatives are going to cancel out. Boom, boom. And I'm looking at 2 over 1 minus 1. So that's 2 over 2 minus 1 equals 2. So my Ki solving in both ways ends up being the same. Now, should that be much of a surprise? No, that's perfect, that's good. But one of the things that you should remember about an uncompetitive inhibitor curve is that these two lines are perfectly parallel with one another. So it doesn't matter if you're looking at the ratio of your y-intercept or your x-intercept whenever you're solving this. All right, well, I hope this was helpful, and I hope this will give you a little bit more clarity on a Ki and solving for a Ki. Have a good afternoon.